Hello. This time I want to introduce a very important and useful concept called flux. Very often we find it useful to have a way to visualize the field lines. And there are two different ways to do this. I'll use the example of gravitational fields still. The first way is to draw the fields in terms of arrows. And the direction of the arrow is the direction of the field, and the length of the arrow represents the strength of the field. So for example, if we had a mass here of, say, m1, then the gravitational field would be a field that attracts a unit mass to that mass. So the direction of the field is going to be everywhere towards the mass. But because the gravitational field is g m1 over r squared, that's the gravitational field strength, the force of attraction on a unit mass, the field strength is going to vary inversely with the square of the distance. So the field strength is much greater closer to the mass and much weaker further away. And we can represent that in terms of the length of the lines. Have larger lines closer to the mass, and as we move away, the lines get shorter and shorter. And we'd end up with something like this, but the pattern continues all the way around the mass. There's a simulation of this available on the website as well. It looks like this. I can add a charge here, which represents a mass, and you'll see that all of the arrows everywhere point towards that mass, and the length of the arrow is a function of the field strength, and therefore the arrows closer to the mass are longer, the arrows further away are shorter. However, there is another way to represent the field strength around a mass, and that is to use this concept of flux. Now, perhaps the best way to think about flux is in terms of a light bulb, or even the sun. The sun is constantly shining radiation out in all directions around it. And if we wanted to draw the light emerging from the sun, we might draw something like this. A sun object, and then these lines emerging from the sun. Typical child's artistic representation of the sun, perhaps. Now, this doesn't mean that all of the light is just emerging in these discrete rays. It's just a way of indicating the direction in which the light is moving. But if you draw the light moving out in these individual directions like this, then you can relate the strength of the light at any point, which corresponds to the field strength, in terms of the number of these lines that pass through a unit area. If I draw a unit area there might be, in this case, just about 5 lines passing through that unit area. If I drew the same area further away, there's only 2 lines passing through it. And it's the density of lines passing through these areas that represents the field strength when you're drawing the fields in terms of flux. These would be called flux lines. And if we illustrate what they look like in the case of a single mass there, they look like that. Again, I must emphasize, that doesn't mean that it's only on these lines that any force exists. Force exists everywhere. The lines are just showing you the direction in which the force exists, in this case, towards the mass. And if you can imagine that there weren't just these individual lines around this mass, but in fact there's an infinite number of these lines going out in all possible directions, then it's the density of those lines, the number of lines that cross through a unit area, that represents the field strength. Obviously, we don't draw an infinite number of these flux lines. The diagram would just be solid blue and we wouldn't see anything useful in it. So we only draw a few of them like this. But that's enough to allow us to interpolate between them and see the field direction at every point, as well as calculating the field strength. One very important point to note about flux is that this concept only works for inverse square law fields. That is, fields whose field strength is proportional to the inverse square of the distance. Fortunately, gravitational fields that we're using in our example, as well as the electric fields and magnetic fields that we're about to come across, are all inverse square fields. I can try and illustrate why the concept only works for inverse square fields. Supposing you have this point charge here, and it's at the centre of a sphere. What is the total amount of flux that emerges from the sphere? Well, as I've said before, the density of the flux, that's the number of lines that pass through a unit area, that represents the field strength. In fact, it's equal to the field strength. So if we take the density of the flux, that's equal to the field strength, gm1 over r squared, and multiply it by the total surface area of the sphere, which, if your distance r squared away, would be 4 pi r squared, that will give you the total amount of flux emerging from the sphere. Density, that's flux per unit area, times the area, gives you the total flux. You'll see that the r squareds cancel and just gives you 4 pi g m1, which is not a function of distance. And it can't be, because if this concept of flux is going to work, then it doesn't matter what the radius of this circle that I draw is, the total amount of flux emerging is going to be the same. All of the flux that emerges from the mass has got to go through all of these spherical shells. And if the field was proportional to anything other than 1 over r squared, then the r squareds would not cancel, and we'd have a different amount of flux emerging from different radiuses of these spherical shells. And that's not going to work with the concept of our flux lines, because lines would have to stop in the middle of space, and flux lines don't. Flux lines only start and stop on masses. When we get to discuss electric fields, we'll find that flux lines start and stop on charges. But they never start or stop in the middle of space. Using these concepts allows us to work out what the field strength is going to be around multiple masses. For example, if I added another mass into this kind of simulation and drew the flux lines that we get in this case, we'd get something like this. The total amount of flux emerging from a sphere around both of these masses is just the sum of the flux lines emerging from both masses. You'll also notice something quite important. Flux lines never cross. They can't, if you think about it, because the direction of a flux line is always in the direction of the field strength. And if flux lines crossed, that would mean that at that point where they cross, the field is in two directions. One along one flux line and one along the other flux line. Well, that makes no sense at all. The field at the same point in space cannot be in two different directions at the same time, which means that flux lines can never cross. So, a quick summary of the important results here. Gravitational force is the force of attraction between two objects with mass. The field strength is a vector. It has magnitude and direction, and its direction is in the direction that a unit mass would move in the field. The gravitational potential at any point in space is a scalar and equal to the amount of energy required to move a unit mass from infinity to that point. Working with gravitational potentials makes it much easier to determine how much energy is required to move a mass between two different points in space. All you have to do is subtract the potentials of those 2 points in space. We also have this concept of flux, which is a theoretical way to imagine what the fields are doing in an area of space. And as we'll see, it allows some very simple methods of calculation for some useful cases later on. Flux lines start and stop on, in the case of gravitational fields, masses or infinity. In the case of electrical fields, they start and stop on charges or go off to infinity. But the flux lines never stop or start in the middle of space. And flux lines never cross. And the density of the flux is the field strength at any point in space. Okay, that's enough for this time. Next time we'll go on and look at electric fields.